just gonna wait, say 1 more minute. I started the stream a bit late. I was messing with the technical aspect of things. Okay, let's make a start. Right. So, um, just to give a quick recap, and always as a reminder, if you go on the channel, you should find playlists available to look at previous lessons, because this will be um, our conservation and dissipation of energy topic that we've done a few lessons on previously. But just as a recap as to what you should have already learned, we've done quite a few calculations so far, and you guys have really done an excellent job on those calculations. And remember, there's some formulas that you got to memorize as well. So there's a few that was meant to be an E. Energy equations. So we had the gravitational potential energy equation. Remember, gravitational potential energy is all to do with height from the ground, which was then we had the kinetic energy equation, which is all to do with the energy stored in a moving object. That's K equals 0.5 mv squared. Remember, m is always mass, the g is gravitational field strength, h is height, v is speed or velocity. And then we also had the elastic potential energy, so energy stored in a stretched or compressed object. And you'll notice that it's very similar to the kinetic energy equation, where K is the spring constant, so how stretchy something is, how stretchy the object is, and E is its extension, so its change in length. And those were the three equations we did when it came to our different energy stores. Now also, another equation we looked at was our work done equation. So work done equals force times distance, and I'm going to put in brackets in direction of force. Because remember, it's like a special type of distance, but right now you can think of it as the same as distance, it's just more specific to in direction of force. Now the reason why I put this equation separate from the others is because I don't want you guys to get confused and think that our work done is somehow different from gravitational potential energy, different from kinetic energy, different from elastic potential. Because remember, it's not. Work done is just what we call an energy transfer when it's transferred by a force. So, for example, let's say a force was used to push something to cause it to move. Well, then our work done would be the same as our increase in kinetic energy. Let's say we used a force to stretch a rubber band, an elastic band. Well, then our work done would be the same value as our elastic potential energy. Say we'd used a force to lift something up. Our work done would be the same as our gravitational potential energy. So work done is just the energy that is transferred by a force. So when you have a force that's transferring the energy, we can use this equation if we know the force. But I do need you guys to understand that work done can be gravitational, can be kinetic, can be elastic, can be any type of energy that we have already discussed. It is just sometimes we talk about it specifically to forces. Also, another thing for you to remember is this equation. You do not have to memorize it. This equation will be given to you. So the elastic potential energy one, you don't need to memorize it, but you do need to memorize GPE, KE, and work done. So that's what we covered so far. Remember, any practice on that along with the answers are on the website. Okay, now we're going to move on to what I call conservation of energy calculations. Now, the interesting thing about these calculations is that you're not going to be using any new equations. So I don't want you guys to panic and think, okay, we have to use some sort of new formula. No, you don't need to do any of that. You're still going to be using all of these equations up here. So these are still going to be the equations that we're going to be using. I'm not going to introduce anything new to you guys. The reason why we have a separate lesson for these conservation of energy calculations, though, is because we're changing how we think about these three equations and combining them using our knowledge of the theory of the energy transfers. So let's start off with an example. An example is always best. Okay. So let's say we had a catapult. Let me just make sure that I have my... So here's an example. A catapult is used to fire an object, is used to fire a 0.2 kilogram object vertically into the air, reaching a maximum height of 5.0. meters. Calculate the speed of the object when it left the catapult. Okay, so that is going to be our example problem. Now, the first thing I want you to point your attention to is because this is a series of events. We're not just like, unlike our previous examples when we calculated for just gravitational potential energy, just kinetic energy, where we're looking at just the change in height or just the change in its speed as it's moving. We're now looking at a series of events. So let's look at the theory first. At the start, I'm going to draw my little object here. At the very, very start of this scenario, it started off with its maximum speed. And it's going up this way. It's starting off with its maximum speed. At the very start, because it's just left the catapult, it's at ground. On the ground. I'm not going to bother with drawing the catapult. what do you guys think its gravitational potential energy is at the start? So right now when it's just fired from the catapult, what is its gravitational potential energy? Um, Good guess. Think about our GPE equation though. Let me actually scroll down to draw this a little bit bigger. So I'll put the equations up here to remind you. I'll go with this color. I'm actually going to draw the catapult this time. Okay, this is going to be launched upwards. Let's pretend this is sort of the ground though, because I know that I have it a little bit high up, but let's pretend this is the ground. So its height at this point is 0. So what do you think the gravitational potential energy is going to be at the very start? If you look at the equation for gravitational potential energy, you'll notice mass times gravitational field strength times height. Well, it's mass from the question. I know it's cut off because I scrolled down, but the mass was 0.2 times by gravitational field strength, which is 9.8, then times by height, which is 0 because it's at the very, very start of its journey. Anything times 0 is going to be 0. At the very start, it actually has no gravitational potential energy, as Lauren said. Hold on, let me just rub this out. So at the very start, its gravitational potential energy is 0, but at the very start as well, its kinetic energy would be its maximum amount, because it starts off with an initial high speed due to the catapult, and then gradually, as it goes up and up, it loses speed as it travels up in the air, right? If you imagine like you're tossing a ball into the air, the point where it's the fastest is right after you tossed it, because that's when it has the most speed, and then it slows down as it lifts up into the air, then falls back down. So at this point, its kinetic energy is maximum. Now, let's draw it like a second later. So there's still my catapult there. Now let's say the ball is by here now, at its maximum height. So if it's at its maximum height, its gravitational potential energy is going to be at its maximum point, because the mass isn't going to change. The gravitational field strength of Earth isn't going to change, but what changed is that h became the biggest possible. From the question, it said it reached a maximum height. So at this point, it's at its maximum gravitational potential energy. But its kinetic energy, if you think about throwing a ball up into the air, there's a point where when it's reached its maximum, it just stops for a second to change its direction to go back down. Right? It goes stationary just for a split second in the air. You can test this now if you have something that's safe to throw into the air, where it pauses in the air just for a split second, and then it changes its direction. So its kinetic energy at this point is actually 0 until it starts falling back down. But we're not concerned with that part just yet. Now I want you to notice what happened here. Things switched around. So at the very start, we had a maximum kinetic energy, no gravitational potential energy. Then later in its journey, when it's reached its max height, GPE became max this time, and kinetic energy became 0. This is what we call the law of conservation of energy, and we talked about this before, where energy is not created or destroyed, it had to have been transferred from somewhere. So in this case, our object gained loads of gravitational potential energy. Well, that gravitational potential energy can't have just come from nowhere. That energy needed to have been transferred into being a gravitational store. Well, now we can see that the gravitational potential energy was transferred by kinetic energy. Here's another example before we go on to the calculations part. Let's say we had a roller coaster. This is just to get you guys thinking about it before we do the calculations. Let's say we had a roller coaster. I'm going to make, for simplicity, I'm going to make my roller coaster short. It is just one hill and then you drop down. There's my little roller coaster cart. Only one person inside. So at this point of the roller coaster, because it's at the very peak, its max height, it's going to be max GPE. Because remember, gravitational potential energy is all to do with height. When you're at the very peak of a roller coaster, if you guys have been on a roller coaster before, when you're at the very peak, you're not moving, you're waiting for the guy at the very top to release you into the fall. So kinetic energy is going to be 0. Right now you're just at the peak. But then as you fall down here, you start picking up speed. And thinking about the energy stores, whenever you pick up speed, you're also increasing your kinetic energy. So by here, in your journey on the roller coaster, your kinetic energy is at its maximum point. Once again, where did all that kinetic energy came from? You started off not moving, your kinetic energy was 0, now all of a sudden you're moving and your kinetic energy is huge, it's at its maximum point, but kinetic energy cannot come from nowhere. Where did that energy come from? Write it in the chat if you can figure it out. Where did that kinetic energy come from? Very good, guys. Exactly. It's come from the GPE. So right now the GPE is going to be 0. So that is the theory behind the law of conservation of energy, where when one energy store increases, you're going to bet that another one decreased by that same amount. Let's add just numbers to this. I'm going to add simple numbers. Let's say that our kinetic energy was 0 at the start. And our GPE, let's say it was specifically, I'm just making up a number, this is a very unrealistic number, do not take me at this and say, Miss, there is absolutely no way that you can only have 100 joules of energy at the top of a roller coaster. Yeah, I know that. Let's say it has 100 joules at the very top of this roller coaster. Then that means that its kinetic energy at the end would have been 100 joules. It had to have been. It can't have been 101 joules, because then that means that 1 joule came out of nowhere. So we can't have had that. We can't have 99 joules, because, well, then 1 joule somehow disappeared into nothing. The conservation of energy basically says that whatever energy something has lost, another energy store must have gained that same amount of energy. That is the law of conservation of energy. So this is how we apply it to calculations. Back to our catapult example then. Okay. I'm gonna need to rub some of this out, so then that way we have room just underneath our question. Okay. So this is how we apply it to calculations. We're going to be using these two equations because in our catapult example, it started off with maximum kinetic energy, and then it lost that energy over time as it went up into the air. Kinetic energy was lost, and gravitational potential energy was gained. Very good point, Louis, and we're going to actually talk about that in another lesson, because as you're exactly correct, it could have also been transferred into like heat from the friction of the tires in the track. That's a very good point. But for these calculations, unless the question says 5 joules was lost to heat, we're gonna, because this question just has gravitational and just has kinetic, we're going to focus on those two instead of it being, we don't want to overcomplicate it unless our question tells us. But you are absolutely correct that in real life, it does get transferred into other places, but the law still applies that the energy had to have gone somewhere into another store somewhere. And whatever the exact amount is, it would have gotten split up. So what Louis is talking about is, let's say we had 100 joules of GPA at the start, and it got transferred, say 90 of it got transferred to KE, and then 10 joules was lost to like heat and maybe sound around the roller coaster. But that is spot on, Louis. Spot on. But as I mentioned, unless a question is going to tell us 10 joules was lost to heat or something like that, we can just assume that all of it was transferred perfectly. Okay, now to how we do these calculations. So once again with calculations, at the very start I always want to make a little list of everything I know, because it's very important that we extract the correct information from our question. If we don't do this bit correctly, if we don't take the time to do this bit, I would say out of all of the student work that I've seen when it comes to calculations, on exams that I marked, everything like that, the biggest mistake is a student using the wrong number for a specific thing. They would just see a number and they would put it and they would substitute it incorrectly. Like, for example, sorry, my microphone cut off then. For example, let's say that a student sees 0.2 and they substitute in that in for height. well then that's the wrong number because 0.2 isn't the height, which is why making a list is so important, because it is where honestly, it's where I see most mistakes. Okay, a catapult is used to fire a 0.2 kilogram object vertically. So that's my first number that I'm given. It did not say mass, but because it's measured in kilograms, I know that that is a mass. So I'm going to write down mass is 0.2 kilograms. Vertically into the air, reaching a maximum height of 5.0 meters. So height is 5.0 meters. Calculate the speed of the object when it left the catapult. So speed equals question mark. Okay. So that's the information I've been given. There's another piece of information though that the question did not say that I also just need to know. Gravitational field strength on Earth is 9.8. Okay. So, there's two ways of doing this. I'm going to show you one way, and then I'm going to show you the way I do it. The way I do it as kind of like a shortcut to combine steps in one. I'm going to show you the first way first because it's easier to understand because it's not a combination. And then at the end you can decide what way you prefer to do. Okay? So let's look at first method, then second method. They're not too much different. It's just basically the second method, my method, combines two steps into one. That's it. So, right. My problem is I don't know which equation to pick because I have gravitational potential energy. I'm given a mass, a height, but they're asking me to find speed. So because they're asking me to find speed, I know at the end of the day I need to substitute things into this formula because I need to find V. Well, they gave me an M, so I can substitute that in. But how am I supposed to find V if I don't even know what the kinetic energy is? Because remember, you can't have like two variables, two unknowns in the same equation. Because we don't know what kinetic energy is, we're not going to be able to find V. Well, let's apply the law of conservation of energy. We can calculate what the kinetic energy is if we can calculate how much gravitational potential energy was gained. Because how much gravitational potential energy was gained, because our ball started here, then ended up here, KE was max, GPE was 0 at the start, and then it swapped around. Because gravitational potential energy was gained, it took its energy, it transferred its energy, it's got its energy transferred to it by its kinetic energy store. So if I were to calculate how much gravitational potential energy was gained, I would know how much kinetic energy it had at the start, because then I know how much kinetic energy was lost. So I have everything I need for the MGH equation. So once again, I write out the formula, and then I substitute things in from my list. So write out the formula first, then insert values. GPE, I don't know that yet. My mass is 0.2. My gravity is 9.8. And my height is 5.0. Then I'm going to stick that into my calculator. Let's do that all in one go. 0.2 times 9.8 times 5. I got 9.8. Did everyone else get the same number? Try in your calculator, just in case I typed it in wrong. I got 9.8 joules. Remember, there's a calculator on most computers if you're on a computer. I just want you guys to be able to follow along with the calculation as I do it. Okay, 0.2 times 9.8 times 5. Yeah, that should be correct. Okay, so this is my gravitational potential energy. Which is how much GPE it was at maximum. So at maximum point, its gravitational potential energy was 9.8 joules. Once again, that 9.8 joules can't have come from nowhere. If gravitational potential energy went from 0 to being 9.8, then that means that kinetic energy must have gone from 9.8 to 0. So, you know that equation that I started on earlier with kinetic energy? We can put in our GPE value for our kinetic energy value. So we can put in 9.8 for kinetic energy because that must have been how much kinetic energy it had at the start, because that's how much gravitational potential energy we had at the end. Because all types of energy, when things get transferred, are linked by the law of conservation of energy. We can't have missing energy amounts. We needed to have the same unless our question tells us otherwise. So, all I've done here was I've substituted in my 9.8 for my kinetic energy, because even though I calculated 9.8 for my gravitational, I know it needed to also have been my kinetic, because that's where our gravitational potential energy came from. It came from the kinetic energy store. Now, as we've done before, we clean it up and then rearrange. So I see two numbers here that I can combine into one to make things easier for me when I rearrange. 0.5 times 0.2. I've put that in my calculator. I got 0.1 times v squared. Now v is my missing thing, so I have to rearrange to solve for it by getting it on its own, meaning I need to get rid of the 0.1 by here. It's times on, so I have to do the opposite. I have to divide by 0.1 instead. And remember, anything you do on one side, you have to do on the other. Divide both sides by 0.1. These two 0.1s cancel each other out. And I'm going to clean the left-hand side up. My 9.8 divide by 0.1. Going to clean that up. 9.8 divide by 0.1. That is 98. So I'm left with 98 equals v squared. But remember, we're not done, because I want what the v was. I want what the speed was. I don't care about speed squared. I want speed only. I don't care about v squared, I want v only. So once again I have to do the opposite, and the opposite of this squared is a square root. So if I square root it, but remember to square root both sides, then I should be left with just plain old v. 98 square root, just sticking that into the calculator. That should be 9.9 if I round it. And then that's a speed, so that's measured in meters per second. So this is the first method. You calculate one of the energy stores individually based off of what information you have. So whichever energy store you have the most information on, that's the one you calculate. And then you take that calculated number and apply that same number to the other energy store because you know they have to be the same, and then just solve for whatever's missing. So this is method number 1. You're just using two equations separately, but then linking them because the energy value, even though there's gravitational and kinetic, they're separate energy stores, the energy value, the number, has to be the same because of the law of conservation of energy. Now here's the second method. If you feel like this is not for you, that's fine. Just use the first method. Both of them work and will get you full marks perfectly fine. But this method, the reason why I'm teaching it is just because it can be a little bit shorter rather than having a long page of work. So, from my question, because I know it's transferring from a kinetic energy store, because it's asking for the speed as it left the catapult, I know that it's to do with kinetic energy, and then I know it gains gravitational potential energy. I'm going to set them equal to each other from the start. So I have my GPE equation. I have my KE equation. I know GPE is going to be the same as KE because of the law of conservation of energy. So I like just doing mgh, which is what GPE is, what gravitational potential energy is equal to 0.5 mv squared. I like just doing that, and then substitute everything in one go. So my list, mass is 0.2. One thing I also want you to notice is that because the mass is the same on both sides, technically you don't really need the mass. That could just cancel out. But I'm not gonna, I'll leave mass there just because I don't want to confuse anyone. So I'll leave it as it is, mgh equals 0.5 mv squared. Let's see if I have a number for m. My mass, scroll up to my list, is 0.2. So I have 0.2 substituted in here. Then I have my g, scroll up to my list, I do have g, it's 9.8. As I remember, on Earth it's 9.8. And then for h, scroll up, my height is 5, so I have 0.2 times 9.8 times 5 equal 0.5 times my mass, once again, is 0.2, it's the same object, times v squared. So this is the way I like doing it. It looks a little bit like all in one go, because it is, but if you're comfortable with it, then it makes things a lot quicker. Cleanup time, put that all in my calculator. That would have been 9.8. On the right hand side, that's 0.1 times v squared, and then you notice you're going to end up with the same exact point as you were before. So notice how this is the same exact point. Square root both sides, v equals 9.9. So it's the same exact thing, the two methods. The only difference is that rather than doing one equation at a time, you're just setting them equal to each other and doing both equations at the same time, doing it all in one go. So pick whichever method that you prefer. It doesn't matter, both will get you full marks. It's just whatever you feel comfortable doing, whatever you feel like you understand better. So we're going to do one more example, but I want you guys to calculate for it. And then I'll go over the answer at the end when I give you a bit of time to calculate. And then I'll give you a link to the practice. Okay, so here is example number 2. A helicopter drops a 20 kilogram package. If it helps, by the way, you can always draw a picture of the scenario. Drops a 20 kilogram package from rest, so basically the package wasn't moving. So it started off not moving at a height of 120 meters from the ground. What is the speed of the package just before it hits the ground? Because obviously when it's hit the ground, it'll have stopped. Okay. So that's my question. Let me then pick. I'll draw a little picture just so you can see. It's going to be a very simplified picture. So here's my package. It's 20 kilograms. Started off about 120 meters from the ground, and then will be right just before it hits the ground, but technically the meters is 0. So it lost all of its gravitational potential energy. Still 20 kilograms. So remember our formulas that we need. You're going to have to memorize these, but I'll write them out for you just at the start. And you can use either method. You can either calculate for one and then just use that number for the other one, or you can combine the two equations to make mgh equals mv squared. You can do that and then just separate and then substitute things in one by one. So there's more to substitute in, but you'll still get the same answer. It's up to you what method you want to do, whether you want to do one equation first, then the other one, or if you want to combine those two. But at the end of it, you should still have the same answer no matter what method you do. So I'll give you a bit of time to have a go at this. No. So with that's a very good question. So basically, what you are missing here, though, where you're going wrong, is let me write out a little bit more. So this is the first stage. So this is at the very start. On the left side, this is at the start. For our object, our package, its GPE is at max. Our kinetic energy, because it started at rest, was 0. And then at this point, just before it hits the ground, our kinetic energy was max, and our GPE was 0. So what you were trying to do then, Lauren, is you were trying to do the height, take the height of the second phase, but you're correct that in the second phase, because the height is 0, the gravitational potential energy is going to be 0, but its kinetic energy is not 0 at that point. So what you're going to have to do is you're going to have to calculate how much gravitational potential energy it started with, and that's going to be the same as how much kinetic energy was gained at the end, because its gravitational potential energy it started with transferred into the kinetic energy store. So once again, making up numbers, say at the start gravitational potential energy was 100, it's not, but say it was 100, then that means at the end kinetic energy would have been 100. So the two separate values, they would have been the same. So this is GP of phase 1 would have been equal to the kinetic energy of phase 2. Hopefully that makes a little bit more sense now. Depends on what you mean by big number, but yeah, it should be a big number, like a big-ish number, and that would have been this whatever number you have for GPE would be then taken to be the same as the kinetic energy in phase 2. So let me just give you the number that you should have gotten for GPE, just so then you can confirm that you're on the right track. So GPE should have been the first thing that you're able to calculate, because you're missing speed, and you also don't know what its kinetic energy was in phase 2. But you can calculate for how much gravitational potential energy it started with. So it would have been 20 for M times 9.8 because of gravity times H, 120. That should have been what you put in your calculator, and you would have gotten a big number. It should have been, let's see, 20 times 9.8 times 120. That should have been 23,520 joules. And that should have been what you got for GPE, but remember, you're not finished yet after GPE. You then have to take that number to be the same as the kinetic energy in phase 2, and then solve for our V, our speed. Is that the number you got, Louis? Oh, 20,000. Is 23,520 what we have? Nice, good work. Now substitute in that value you got for gravitational potential energy into our kinetic energy, and then rearrange to solve for our speed. I'll give 1 more minute on that just to give everyone a chance to get as much, to be able to get it done. Okay, let's go over the answer now. So, once again, I know because of the conservation of energy, in this case my GPE at the start was 23,520 joules. And kinetic energy was 0. At the end, kinetic energy gained and GPE became 0, so I know that that would have been the same number because of the law of conservation of energy once again. So I use my kinetic energy formula now, substitute in what I got, what my gravitational potential energy was for kinetic, times not, it wasn't 0.2 anymore, it was 20 times v squared. I'm going to combine those two into one number to clean it up a bit. That's 10 times v squared. Do the opposite, so that's 10 times. That means I'm going to divide by 10. I'm doing that on both sides. So it would have been 2352 is equal to v squared because those two tens cancel. And then I square root it at the end because I want v, not v squared. Some students forget to do that step. So 2352 square rooted, that would have been 48.5 when it's rounded. So v is 48.5 meters per second. That means right before the package hit the ground, it had a speed of 48.5 meters per second. Hopefully we're happy with that. Okay, so I'm going to just link to some practice now. for those of you who have gotten that number and are happy, I'm going to put all of the answers up in a second. But once again, this sheet is optional, so you don't have to do it. It is just about you, like, I'm not assessing it or anything like that. You don't have to submit it to me, but it is just about you developing a sense of confidence in what you're doing. So the first, if you open that up, the first set of questions in question 1, a cyclist cycles over a humpback bridge. There's no calculations in that. That sort of question is about, do you understand the relationship between kinetic energy transfers and gravitational potential energy transfers? So thinking about at what point is GPE the max, at what point is KE the max, so on, so on. Question 2 is some calculations. Everything else is just calculation, but multiple parts. So really, really think about the question and what you have to calculate for. Remember, the two equations that you need are just the kinetic energy ones and the gravitational potential energy ones, and it's just about picking and choosing depending on what information you have. Alright, so those answers are going to go up, the answers to that sheet are going to go up in a moment. I just need to have it written out and uploaded. But you should be, by the time you finish, if you get started, you should be able to see how well you have done. And remember, if you lose the link to that, if you just go on the website, remember to put it in favorites or something, just so then you can always go back to it to check for resources. The link to the website is there, and you click on the Conservation of Energy section. And if you say come back to it later, decide to come back to it later. But I'm hoping we all got 48.5 meters per second. And yeah, good work, because I mean, think about it. At the start of the lesson, if I said to you that you'd be successful at combining that and that, combining those, I mean, look at it. It looks hard, doesn't it? But you guys have done it, so really, really well done. It is just about the understanding that the different energies, even though they're different energy stores, they're still linked together by the law of conservation of energy. That is the key. And as long as you understand that the different energy stores are linked, you will be golden. Alright? So that is it for today. The answers are going to be put up soon. Have a go at those questions. You don't need to submit it back to me, but hopefully we feel a bit confident with those calculations. When I put the answers up, if you're not really sure how I got a particular answer, leave me a comment on Show My Homework or on the video when it uploads, or send me an email. I'm happy to respond, or I'm happy to next lesson go over the question, or even make a separate video for a question that you were struggling on. That's completely fine by me. Okay? Right, guys? Have a good rest of the day, and enjoy. The answers will be put up soon.